Alright, so what we're doing here is we are developing the algebraic formula for dot product in 2 space and 3 space. So if you're using, for example, a coordinate system of A1, A, which is a combination of A1, A2, and B, which is a combination of B1, B2, we can determine the component vector for A as component of A1, A2, and vector B as component of B1, B2, such that the dot product of these two is A1, B1 plus A2, B2 in R2. And the dot product in 3 space would just add a third component. Now, we also need to know that using the dot product of what we learned, the geometric dot product, we can define cos theta as cos theta is equal to the dot product divided by the magnitude, the product of the two magnitudes of A and B. Next, looking at example 1, we're going to state the angle between A and B when vector A is equal to a certain component vector and vector B is equal to a certain component vector, such that we need to determine the angle between this. In order to do that, it's important to take the formula that we just developed about cos theta and find the magnitudes of A and B, such that the magnitude of A is equal to root 14, magnitude of B is equal to root 26, and we determine using the dot product the values that we're looking for. So, here we go. Looking at the dot product of A and B, we use the calculation that we determined algebraically to find out that the dot product is equal to 13. Cos theta is equal to the dot product divided by the product of the magnitudes. If we do that and fill in the information, we find out that 13 divided by root 14 times root 26. And this, if you note, you multiply both the top and the bottom by root 91, you find out that you get root 91 over 14. Finally, if we look back at that last question, we could determine what value of theta is by taking the cos inverse, which I'm assuming that you all can do. Let's go to the next question. In this question, example 2, we need to prove algebraically that the dot product of a sum is equal to the sum of the individual dot products. So what we do is we set it in 2 space for practicality's sake. So we have A and B and C in 2 space would be considered A1, A2, B1, B2, C1, and C2. And we also need to note that vector B plus vector C is equal to the components of B1 plus C1 and B2 plus C2. Now, let's look at the right side. You see that A1, B1 plus A2, B2 plus A1, C1 plus A2, C2. This is the algebraic representation of the dot product of A dot B and plus A dot C. Now, rearranging it, what you'll notice is we're going to combine the A1s so that you have A1, B1, A1, C1, plus A2, B2, plus A2, C2. Now, if you look carefully, you'll see that A1 can be common factored from the first two, so that you're left with B1 plus C1. In the second part, you'll note that A2 can be common factored, so that you're left with B2 plus C2. Note that I've highlighted the A, the B, the C, and the B plus C. You should note something interesting, that this expression that we just found is equal to the dot product of A dot vector b plus vector c, which turns out to be our left-hand side. Last question, or next question. Given vector A is equal to 5, 6, and 1, and vector B is equal to k, 4, and negative 3, you're asked to find the value of k such that vector A is perpendicular to vector B. Note that if vector A is perpendicular to vector B, then the angle between vector A and vector B is equal to 90 degrees. This is important to note. So once we note this, we know that the dot product of a particular formula of two perpendicular vectors is going to equal something unique. So A dot B is going to equal 5k plus 24 minus 3, so this is the algebraic representation, equals 0. Why is it equal 0? Well, note that the cosine of 90 degrees is equal to 0. So, solving for 5k, you find out that 5k equals negative 21, and k is equal to negative 21 over 5. You could use a decimal for this answer because it is an exact decimal, but I don't recommend it. Please try and keep your answer in fraction form as much as possible. Let's go on to the next question. In example number 4, you're given that vector A is equal to m negative 7, vector B is equal to m negative 2 and 9. Find m such that vector A is perpendicular to vector B. Try this question now before I give you the answer. Stop the video now. Alright, here goes. You find out that vector A dot vector B must equal, obviously from the original definition of dot product geometrically, and now note that theta is equal to 90 degrees, so cos theta is equal to 0. So using dot product algebraically, you get that m squared minus 2m minus 63 is equal to 0. So what's important is to note what you have there. You have a quadratic equal to 0. You should try to factor first. And once you factor, you find out that m minus 9 times m plus 7 is equal to 0, and that satisfies the quadratic. M equals 9 and negative 7. So the values of m, it's more than one value. You have vector A component is 9, 9, negative 7, and vector B component is 9, negative 2, 9. Or, if you're substituting the negative 7, you get vector A is negative 7, negative 7, negative 7, and vector B is equal to negative 7, negative 2, and 9. Interesting. Next, for example number 5, state a vector perpendicular to vector A and vector B. Now, before we start this question, pause and let's think about it. Alright, what you have is that if a perpendicular, then the dot product is equal to 0. Remember that. That's one of the properties that you have to keep in mind. Vector V, let vector V equal x, y, and z. What does that mean for us? Well, vector A dot V is equal to 0, and vector B dot V is equal to 0. Okay, note that vector A dot V is equal to x plus 7y minus 2z equals 0. Vector B is equal to 3x minus 2y plus 5z equals 0. Make the first one equal question number 1, second number equal equation number 2, such that we can use elimination to at least isolate for one variable. And we find out by subtracting the various applications to the two equations, 3 times equation number 1 and equation number 2, we take 3, take away 4, and you find out that 22y minus 11z equals 0. Well, that will give us a solution that z is equal to 2y. Substitute this value in equation number 1 and you find out something unique for x. X can be expressed in terms of y as well. So we find out that x equals negative 3y. Well, what's very important now is that we set up the perpendicular vector in component form. In order for it to be in component form, we cannot use the letters x, y, or z. So note, you let y equal t, so we set a certain parameter such that t belongs to real but not equal to 0. So this is the solution to the problem. Thanks. I hope this helps, folks. We'll see you tomorrow. Bye.